right, welcome to the last session of DevTernity, at least on track 2. Hope you had a great conference day so far. Everything good? Great. Woo! Yeah, I hope the next 50 minutes won't be disappointing to you as well. We're going to talk about advanced mixed reality development and best practices with a strong focus on the HoloLens. And so first of all, I'm going to show you some use cases and some applications we developed for the platform, and most importantly, share the best practices and lessons learned. But this will be kind of a past-present perspective. And then we will quickly switch into the future of mixed reality, where we bring in AI, and I'm going to show you a demo, and you will also get the source code of that, where it's running a deep learning inference for near real-time object recognition on the HoloLens. And then at the end, we will conclude it with my top 10 mixed reality development recommendations. My name is René. I'm Director of Global Innovation at Valorum Reply, and we've been working with virtual reality, augmented reality, mixed reality, extended reality, whatever reality, choose your terminology, since many years, in particular with the HoloLens since 2015. So we got early access and since then developed multiple applications for different clients and various verticals. So I'm going to show you a couple of those. At the moment, my focus with my team is on a piece we call Holographic, which allows you to do 3D volumetric video streaming. So think about like a real-time hologram. And I'm going to show that to you as well. I'm also a Microsoft Regional Director and Most Valuable Professional, which are kind of awards and recognitions by Microsoft for independent experts. So I don't get paid for Microsoft for being here. I just enjoy, speaking and sharing the knowledge, and that's being honored by Microsoft with those awards. Just a couple of words about company I work for, Valorum. I'm headquartered in Kansas City. Most of the team for Immersive is actually in Seattle. I am located in Germany, in Dresden. And we don't just do Immersive, it's like the full stack, like back-end to front-end, but my team's focus is really on 3D and Immersive development. Quick video, it's going to show you a couple of team members, also especially some of the HoloLens applications we developed. And it's less than a minute, but it's quite fun. Okay, enough of the marketing. Let's get started. Lessons learned. I just picked a couple applications for the sake of time and for the interest, I think, here. Alright. Like, this screen seems to be not working too well, so if you guys want to go over to this side, I should reduce the resolution. Okay, let me try that real quick. Lessons learned. Yeah, there we go. All right. So what would you recommend? What kind of screen resolution? Is that better? Not really. Let's go with that. And yeah, it's great if you could go just move all there. Appreciate it. All right. All right. Yeah, sorry for the inconvenience. Okay, well, this is an app we developed together with Bridgestone. So as you can see, it's augmenting a tire. Doesn't sound like very fun, but actually it's pretty nice because, well, we can use that technology to help actually sales folks and, for training scenarios and so on. So let me quickly play the video and explain to you what it's all about.
Welcome to Tire Explorer. Before we begin, please gaze at the tire.
So this is my colleague Rod. He's a real person, but we use our Holobeam tech to also use it for these kind of tutorials, right? But now take a look at the gentleman that's wearing the HoloLens as he's looking at the real world tire. Now you see this overlay, right? This virtual overlay on the real tire.
Major components that make up a tire.
And there's no AR code, there's no marker on it, right? There's no fiducial QR code, anything like that.
Air tap any component to learn more.
What we're using here is a piece called Model Targets. That's from Bavaria, and it's an API available for the HoloLens, but also available for other platforms like Android and iOS and so on. The nice piece about it is you don't need to use a fiducial marker, right? No QR code, no weird AR tag. You can actually use a real-world object as your marker for tracking. So what we did is we got a model from Bridgestone, like a CAD file, and then we optimized that a little bit and use that as our real-world marker. So we don't have to use any fiducial overlays and stickers on top of that, which most clients really don't want, especially when they're exhibiting their products, right? Lessons learned, especially for the model targets. Well, HoloLens has quite some constraints when it comes to rendering power. I'm going to talk about that later on. But definitely when you get one of those CAD models with millions of polygons, that just doesn't work. It's way too much. So we had to reduce that. So we reduced the model size quite a bit, throw out some detailed polygons. And also for the stuff that is part of the model. So for example, Bridgestone, of course, they just manufacture tires, right? So we didn't get a rim. But we added the rim to the 3D model, so we had a bit more stuff to track for the pattern recognition. Also, you see the lamp there with the lighting. So we had to install that to have more contrast on the outer rim, so it tracks much better. So a couple of lessons learned. I would say definitely Model Target is an awesome piece because you don't need AR markers, but you need to optimize your 3D model that you're going to use for the pattern recognition. All right. Second one is the quite high-end rendering we have for the
Before we begin, please
for the tire components. As you can see here, there's some pretty nice visuals on top of that. And that's all developed with custom shaders. So if you don't know what a shader is basically a small program that runs on a graphics processor. And if you have a pixel shader, for example, that's executed for every pixel, right? And since the HoloLens is a mobile device, no tethering, fully self-contained, so all the computing is done on that mobile device, you need to optimize it quite a bit. So what we used to create those shaders, we used a tool called ShaderForge that basically allows you to have graph-based editing. So you basically have, you don't have to write the shader code all by hand, right? You can use some graph-based editing. Actually, the good news is it's now free and open source, and actually also Unity, the Unity 3D engine, they have their own shader graph-based editing tool now integrated. So you can just use that. But lesson learned, of course, you need to optimize the generated code, right? The shader code these tools generate is pretty good start, but definitely not something you can use in production if you want to get the last pieces of performance, right? So you still need to take a look into the results and hand-tune those.
Welcome.
All right. Next one. That's a piece we did for an automotive manufacturer using a machine learning backend for object recognition, right? So you see the guy here wearing the HoloLens. So what he does with this air tap gesture, right? The HoloLens recognizes those gestures. He basically taps. We take a photo, what the user is seeing, like this one, send it to a backend that does the object recognition. For example, disc brake is being recognized, and then we pull in contextual information and show that in the field of view in a panel to the user, right? We can also play back setup videos or videos that show how to assemble or disassemble. The good thing with that is with devices like the HoloLens, which are fully untethered, there's no cable, right? And the user is basically wearing a computer on their head with transparent screens. So they have the hands-free for real tools. That's what I call hands-free computing. So you can really use your real-world tools and do the real work. I'm showing that because later on I'm going to show you that we don't need a backend for this stuff anymore. We can run the object recognition now on device, which is really important for these kind of settings, because the lesson learned here is definitely in those factories, there's many, many signals, and internet connectivity is typically challenged. And when you upload a picture, right, it's not just a text snippet. So there's quite a bit of involvement. So latency can be a problem. But now, like I said, I'm going to show you how you can do that on the device and don't have any latency there. All right, Holobeam. I hinted at it. That's our real-time volumetric video streaming solution. Now let me play the video so you see an example. That's actually me beaming from Dresden into the New York City store in real time, and we just use 5 Mbit, right? So what we're doing here, I'm going to explain it in the next slide, but basically we're using adaptive streaming, which means if the bandwidth is lower, we lower the quality, but it still works below 1 Mbit even, right? Yeah, you can see a 3D representation of that person. Think about, I call it Skype on steroids. It's really, it's a 3D video, right? It's not a 2D video, it's not like flatland, it's really your 3D world. All right. Yeah, the nice thing, that's a good point. I'm going to show that to you maybe as well. It's all dynamic rendered. It's all dynamic point cloud. So we actually have full control over it. So we actually have some styles where we can change the filter modes. And of course, we're all geeks, right? So we had to do like the Star Wars effect and the green tinted stuff. And yeah. All right. So here's how it works. By the way, you see this guy, he's wearing a HoloLens with a special accessoire. So you can buy that from our friends at Trimble. You probably know that company. Basically, they have this hard hat accessory so they can use it on a construction site. Also, the HoloLens kind of visor is actually certified as security glasses. So that's a benefit. But of course, you don't have to, right? So that's just one nice piece. And especially if you do a lot of demos, like this hard hat accessory is super nice because people sometimes struggle to put it on and adjust it. And this one, you just put it on the person and it's like pretty much good to go. All right, so how does Holobeam work? We have this 3D camera. This here is a Kinect V2. You might know it from the Xbox. And that provides us not just the color stream, not just the RGB data, but also the depth data. So basically the distance to each pixel, right? And we take those, and then we have a computer here that is connected to it. And our application is running on, which basically takes that stream and encodes that in real time as a real-time video. And what we use here is kind of a bit of a secret sauce is how we can compress the depth data in such a way that it doesn't have a lot of compression artifacts when we decode it. Because that is definitely a challenge because you cannot just apply your typical MPEG block compression algorithm. Because what would happen is, for example, if your hand and other stuff has the same distance, right? And then you decode, encode that, and decode that, you can have quite a bit of artifacts. So your hand might be behind you and things like that happen. So we encode that, stream that real time into a viewing device like the HoloLens, for example, but could also be a virtual reality device, right? And then on the VR device, we reconstruct it in real time. For the actual transmission, we're using a fork of WebRTC. If you might know that, web real-time communication, it's pretty much what the industry, well, not industry standard, but like WhatsApp uses it, Facebook Messenger, they all use that for video chat under the hood. And we forked that because we applied some custom stuff. For example, on the HoloLens, like I mentioned, a fully mobile device, which means rendering capabilities and processing powers are quite limited. So how do we actually decode the video in real time and render that in real time? Well, we use Windows Media Foundation, and basically you do the video decoding all on the GPU of the HoloLens. And then we decode those that video stream into 2 frames. So one RGB frame, one depth frame, and then we fed that into a geometry shader. So it all stays on the GPU, right? It doesn't move back to the CPU. It all stays on the GPU, and that's how we can get that performance and real-time point cloud rendering, basically. And the geometry shader, like I said, gets those 2 textures, and then, well, we do a bit of math to actually map them, because we also need the distance for each camera for depth and the RGB camera. So there's a little bit of math involved here. Most of that, like the network layer and, all of that is in C++, but we surface that via plugins into Unity. So actually for the front end and all of that, we use the benefits of Unity, of having this really nice tool. Well, here's another video. Was shown at one of the keynotes at
a prototype
Ignite.
Of a 3D holographic meeting experience built by Valorum, a Microsoft partner. The cameras behind us here are so that everyone in the meeting room can see the same 3D experience that Ashley and Vivek will see.
Hey, Vivek.
Hey, Ashley.
So this guy is in a whole different room, right?
You had a chance to take a look at that smart buildings pilot
Matt was picking up on
And
some
yeah,
weird
so he's sitting
occupancy
at this
data
conference
from the Power
table
BI
as a
dashboard.
hologram, as a virtual
Yeah,
person.
about that. Let's take a look at the building.
And so what we also support is not just that you can see the
As
other
you can
person
see,
as a
I've
3D
overlaid
video,
various sensor data
but we can
onto
also
the
bring in
building.
3D content. So we can bring in 3D
You would
models
notice
and you can
something very
collaborate on
interesting
those, right?
when I run the time lapse
So think
of the
about
day.
your distributed team,
Pay
your
close
engineering
attention
department, you
to
need
the end of
to,
the building.
I don't know,
It was
review 3D
dark
models and
in the
stuff.
afternoon.
And doing that in 3D while actually seeing 3D content is much better than just looking on a 2D screen, right? So
That's
couple
those
of use
rooms that were
cases
showing up
there.
on Occupied.
All right. So what's next? Well, like I hinted at it, AI is, of course, entering every field basically of programming or software development. But this is Alex Kipman, the inventor of the Kinect and the HoloLens, technical fellow with Microsoft, and you can see what he wrote there. But of course, it's not just cloud-assisted AI. What's also important is like bringing that on the devices, or like this new term is like AI on the edge, right? Basically running it not cloud, but on your local device. That's what I'm going to show you. But first of all, let's clarify what we're talking about here. Because AI and artificial intelligence is such an overloaded buzzword at the moment, right? So what kind of AI are we actually talking about? So AI has a subset, which is called machine learning, right? So that's a subset of AI. And the subset of machine learning are deep neural networks or deep learning, right? And especially when we think about perception, like computer vision, object recognition tasks, all the amazing progress is all happening with deep learning and deep neural networks these days. So how does it work? Just a quick primer, really in a nutshell. We won't have time to go too deep into that. And at the end of my slide deck, I will have a slide with a bunch of links. You can find out some more following information. So artificial neural networks, well, it tries to simulate an animal brain, but very, very abstract, so it doesn't even get very close to it, right? But what you have is, you have all those neurons, if you will, and in our artificial neural network, these are computing functions, right? And the synapses are basically connections between those computing functions, which store a floating point value, a weight. And what you do is, typically these days, it's supervised learning, so you need to have a training data set. And for image recognition, like perception tasks, typically you would have a bunch of photos, which each one is labeled, right? And so then you run that through the neural network, through all the layers here, and then you compare the output, the actual output, with the desired output of a training data set, compute the difference, and then backpropagate the error. And basically what the error backpropagation does, it adjusts those values, adjusts those weights, until your actual output compares to your desired output. And that has been, you need to do that for like many, many iterations, thousands, even millions, or epochs. And once that training step is done, and your neural network is well generalized, it can detect objects it has not seen before, right? And that is called the inference phase. Basically, you have a pre-trained neural network, and once it's trained, it enters the inference phase, where we can give it data it has not seen before, and it will hopefully predict the correct output, right? Just as a primer. So the good thing is, the inference, we can now do that also on device or on the edge, right? So we don't have to do that on a powerful computer. And Windows introduced a piece called Windows Machine Learning, an April 2018 update, or RS4 update. And that allows us to actually have an abstraction layer. So it's really an easy interface to use. And the nice thing is, when we look at the underlying structure, it's actually leveraging a GPU acceleration, right? So if your GPU supports DirectX 12, the inference will actually run on the GPU hardware accelerated. Or even better, like in the future, next couple of years, we will see more and more accelerator chips coming out just specialized for deep learning inference, right? I think pretty much every mobile phone will have it. I mean, if you look at the Apple devices, they all have their inference chip already. So that allows us to run very fast inference on those specialized chips, right? But we don't have to worry about all those layers below it. The nice thing is, we can use best of both worlds. We can say, okay, I use the immense computing power of the cloud or my beefy desktop machine for the training. And then I can use the very short latency and specialized inference chips on my edge device for the evaluation. So I have a very short latency. Alrighty, enough of the theory. Let me show you a demo. Typically, I would take out my HoloLens, put it on, live stream what I see with the lens to my computer, so you see that. But the issue here is, since I'm using the camera already for the object recognition, I cannot use the same resource at the same time for the live streaming. But I can record a video. So I'm going to show you a video which I recorded at home that is showing you the demo in action. Then we will switch to Unity and Visual Studio, going to show you a little bit of code. And then you will also get the source code, of course, for that on my GitHub page. All right, take a look.
This might be a car wheel 3.5 meter in front of you.
So what I'm using here is a so-called SqueezeNet neural network model. It's pretty small, optimized for mobile.
This might be a matchstick 1.1 meter in front of you.
And I trained that on the ImageNet database, like it can detect 1,000
This
objects.
is likely a minibus 3.1 meter in front of you.
Which I customized. For example, it can detect my bus for my car.
This is likely a Volkswagen Multivan Generation 6 3.2 meter in front of you.
All right. For the distance, you hear like this is blah 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 meters in front of you. I'm just using the spatial mapping of the HoloLens.
This is likely a car mirror 96 centimeter in front of you.
Because the HoloLens has this depth sensor where it can actually measure the distance to object. That's what I'm using here. So as you can imagine, of course, we know what this is, right? But think about specialized tools, specialized use cases where your workers don't know what this is, and we can give them this technology, and it can automatically recognize, and you can bring in your favorite beer brand, for example, as well. And
this might be a Raidburger beer bottle 1.2 meter in front of you.
Almost time, huh? 1 hour or something? All right, I think you get it.
This might be a notebook 84 centimeter in front.
So here's a really nice thing with the RS5 update, the latest Windows update, basically. They also ship it for the HoloLens. And what they ship is, as well, a DirectX 12 driver for this 4 or 5-year-old Intel Atom chip. It's kind of crazy, but it's awesome because this allows me to run the inference GPU accelerator. So if you take a look at this top one with the coffee mug, you see the CPU is maxed out, and one inference run takes like 760 milliseconds. So the same with GPU acceleration enabled down here, you see the GPU being maxed out here, but it takes like 4 times, it's 4 times faster basically, right? Because it's running on the GPU, and you can have near real-time inference. And again, that's running on your general-purpose GPU, right? Now think about specialized chip next couple of years. So this stuff is becoming really fast in real time. Okay. Again, I will have a slide at the end with all the links, so if you want to grab a photo of that at the end, I would recommend that. Let me jump to Unity, give you a quick overview of the scene. So who of you have used Unity before? Quick show of hands. All right, not that much. Unfortunately, we won't have a lot of time to dive too much into the details here of Unity. But if you don't know, it's basically a 3D engine with a nice tool in front where you can have your 3D visualizations built in that tool. So really, that's just the status text you have seen in the video that's attached to the main camera. In the case of virtual reality or any device that is a head-mounted device, like the HoloLens as well, the main camera is basically the user's head, right? So that will get adjusted. All right, you have the status text, and then we have our DNN model, which is just an empty game object. And what I have attached here is a DNN model behavior. This is the script that runs all the logic, which I'm going to show you right now. But before I do that, just quick spatial mapping collider here. This is used for the measuring the distance. So basically, the HoloLens, like I mentioned, has this depth sensor that can measure the distance to objects, and then it can reconstruct it as a mesh. That's called a spatial mesh, right? So I can also use it for physics. So basically what I'm doing here to measure the distance, I'm just using ray casting. Basically shooting a ray from the camera, the user's head, into the scene where the ray hits the spatial mesh, I have the distance, right? That's the simple way of doing that. All right. Also important here in the project window, there's this resources folder. That's a special thing Unity uses. Basically every stuff that's in the resource folder will get deployed with your app package workload, right? So that will be deployed in your binary. What I have in here is a JSON file that's just mapping the index of the output neuron to a human readable string. For example, if my neural network, I don't know what, let's pick one, like index 65 fires, I know it's a sea snake, right? There's a bunch of animals in here. So that's the ImageNet database, like I mentioned. So, like I said, 1,000 images, which means my output layer of my neural network has 1,000 output neurons, right? And that's really just mapping the index when it fires to something a human can read. And then we have our Onyx model down here. So Onyx is this format that basically stores a pre-trained neural network. And the nice thing is it's open source, it's an open standard, pushed forward by a couple of industry companies like Amazon, Facebook, Microsoft, and a few more. And it defines this open standard. And the nice thing is WinML supports Onyx, ONNX, right? So I can use that standard format to actually have this WinML inference running. All right, let's switch over to Visual Studio. That script I mentioned. So that's our DNN model behavior script here. And that's derived from mono behavior, which is this standard kind of Unity behavior. And it allows you to implement a custom methods like the start method. And the start method, for example, will get called once your object is being initialized the first time. So basically that's the initialization code, right? What I do here, load model, basically loads the model. I wrote a custom class there, load model async. So let's quickly jump to that one. And what it does is, first of all, we're parsing the string from the JSON file, put that in a list. And then we do a bit of Universal Windows Platform stream IO, which is really a mess, to be honest. Like UWP streams is really, wow, that's not fun. You can see. I mean, that's all the lines will need just to get like a byte array into the memory. It's ridiculous. But anyway, that's what we have to do. So then we have our memory stream with our Onyx model loaded. And then we can actually call our Windows AI machine learning function or method load from stream async, right? So we can pass in that stream. We get our model. And once we have our model, we can initialize a session. And as you can see, the session doesn't not only take the model, but also the device kind, right? So we can actually say, okay, is the device kind DirectX, so runs on a GPU, or is it CPU, right? So we can define that manually as well. And then I'm doing a little bit of other requests here to actually get the input. That's the input description of our neural network. In this case, it's basically the image size that the neural network expects, right? Because we have that fixed structure of that neural network, and it expects a certain size, like basically the input layer of the neural network, right? It has to be a certain size. So I'm just reading out that metadata here. Same thing for the output description. All right, let's switch back. So we loaded the model, then we initialized the camera. So what I'm using here is an API called Windows.Media Capture. That's pretty nice because it allows me to actually use the camera at the same time for the object recognition while I'm also recording the stream, right? Otherwise, I wouldn't have been able to record that video I've shown earlier to you. If I would use, Unity has a cross-platform API, the webcam, but that doesn't work in that sense. So it's an exclusive resource for Unity. So I had to go down to the actually Windows implementation. And what you can see here, I'm actually passing in our deep neural network input width and height. So I'm passing in the size of our input here. So I'm requesting the correct frame size from the camera. The nice thing with WinML is actually, I would not have to do that. It would actually allow me to pass in like a larger size or a smaller size and would automatically scale and crop it to the correct size the neural network expects. But since I can save a couple of cycles here and have the maximum performance, I know the size, so I can already request the correct size from the camera, right? All right, so we have our model loaded. We have the webcam initialized, a little bit of background task here. So basically, I'm running that on a background thread. I'm getting the latest frame from the camera and passed it into this video frame, and I passed it into my evaluate frame method, which is just here. So that does the evaluation. I check the result. If there's a result, I actually need to switch back to the UI thread because I'm running on a background thread, right? And I want to update UI elements. And so I need to switch back to the UI thread. A little bit of string formatting here for the output. But this one is interesting because I'm using a class called text-to-speech that is internally leveraging the Windows 10 speech synthesizers APIs, which means I can just give it a string, like here. Oops. You see, it's really just expecting a string as input, and it will have text-to-speech output. Really simple API. And that one is actually from the Mixed Reality Toolkit, nice open source project by the community that basically connects the Unity audio source world with the Windows 10 built-in speech synthesizing APIs. All right, let's switch back to the presentation. And again, I would recommend, if you're interested, check out the code in depth yourself. There's a couple of things, but I just highlighted the main important pieces. Okay, top 10 mixed reality development recommendations. Actually focused on the HoloLens quite a bit, but they also apply to other virtual reality platforms as well as other mixed reality platforms like Magic Leap and whatnot, right? So it's not just based for the HoloLens. Well, first of all, it's a mobile device. Like I mentioned, it is awesome that it's not connected to any wires, so that you're fully self-contained, can freely walk around. But of course, that also limits the rendering, the capabilities of it, right? So it's not you cannot expect your full-blown graphics card you have on your desktop. So you have smaller budget for rendering, basically. Most importantly, like every mobile device, it's fill rate bound, which means if you render the objects very close to the user's eye and they fill basically the whole screen, and your pixel shader is very intense, the frame rate will go down rather quickly. And what you want to have is you want to at least have 60 frames per second stable, because otherwise when the frame rate drops and the rendering doesn't keep up, the virtual objects, the holograms, start to jitter, right? They start to jitter and are a bit laggy, so you really want to avoid that. So what you need to do is optimize your pixel shader. Don't use the Unity standard shader. That's way too intense. Use a very simple one. Sometimes, of course, pre-baked lighting is pretty good, which means you compute the shading and the lighting before, right? So you don't do that real time. You do that before and really just show the texture on top of your 3D model. And also you want to avoid overdrawing, which basically means, like if you render multiple objects one after another, well, the pixels need to be rendered multiple times, right? So you really want to avoid that. That's actually a general recommendation for every mobile device, like Android, iOS, and whatnot. You really want to avoid that, especially with the high resolution we have these days. But it's not just about the pixels and the fill rate, it's also about the polygons, right? Especially when we think about the scenarios where this technology is being used these days, because we have a nice price point in a sense that it's quite expensive. So it's not consumer, right? It's not a consumer market. So which means is a lot of use cases we see are real enterprise, professional use cases. And what that also means is a lot of these companies, they work with CAD, with CAD models, right? And you have these CAD models, when you tessellate them, there are millions of polygons, like huge models, right? And you cannot render them as they are on a mobile device. So what you need to do is you need to optimize them. I actually gave a talk about that at the Vision VR AR Summit, like what are kind of the ways you can do to optimize those models. And in a nutshell, basically you can use a manual reduction. So you give that to a 3D artist, for example, that takes that model apart and removes the tiny details that are not needed. Or you can do automatic reduction. There are a couple of tools in the market. Unity has a good, partnership with Pixies. They have a very good tool which does automatic reduction, right? It basically checks, okay, what's my threshold? I have like this angle and like this short polygon, this short line, so I collapse them. Like that's basically how they work. Of course, it's a bit more sophisticated internally. Microsoft acquired Simplygon, like, when was it? 1 year ago. It's another automatic reduction tool. And then, of course, what you can also do is you can not reduce your models and use something else, which I'm going to show you in the next step, which is offloading. So you can basically use holographic removing, which means, well, let me show you the video. That explains it a little bit better. So what you see here in the video in the front is what I'm seeing with the HoloLens, right? And in the background, you might be able to see my computer there, right? And as you can see, this computer is rendering the same scene. By the way, these are meatballs. And yep, so you can see the scene rendering there in the background. So what it does is basically it just takes the input from the HoloLens, like the gesture input, the head rotation, the position, and so on, sends that all Wi-Fi to the computer, and the actually rendering is performed on the computer, which of course has a much more powerful graphics card. And then it streams back the video, while basically the rendered frames for the left and the right eye as a video stream. That's really nice, but there's an issue. You see, actually, you might be able to recognize it's running in Unity, right? So what you had to do is you had to basically run the scene in Unity, right? And of course, latency can also be an issue. So here's the good news with Unity 2018.2, the most recent stable release from Unity. You're actually able to use standalone holographic removing. If you take a look, I'm just opening an app on my Windows start menu, right? So it's running here. And pretty good latency, actually, in fact. So you don't need to use Unity. You can actually export an application from Unity that just runs standalone on your computer that automatically detects the IP address, and then you can basically connect with it. And you see there's almost no latency. And of course, this sample is really easy, right? Just a gray colored cube. But think about you use your real big architectural model with millions of polygons with some really high-end shading. And that's actually a pretty compelling use case. The good news is you can actually, if you have a good Wi-Fi connection with very short latency, you can even run the rendering in the cloud. So there are some beefy, NVIDIA machines available that have multiple graphics cards, and well, then you can render like a 50 million polygon model, whatever, right? As long as you have a good latency and that is very short, you can use that quite well. Design in 3D for the holographic frame. So, what we see these days is a lot of 2D UI design still in the 3D experiences. So if I put on a virtual reality headset or a mixed reality one like the HoloLens, there are still a lot of apps that use 2D panels and 2D UI paradigms. But in fact, I'm wearing a device where I can see 3D content. So why am I not using a 3D UI design, right? And that's really what we're switching. For example, with HoloBeam, we rebuilt the UI totally from scratch and come up with some new paradigms for 3D UIs. Holographic frame is also important. Some call it the field of view. So basically, as you might know, the HoloLens, it doesn't have like your full field of view, right? It has those screens that are like this big, and that's where you can see the virtual content, right? And that's a hardware constraint we cannot change, right? But we can work around that. And here's an example what we did for an app. So we allow the user to initially place the 3D model, but we only allow the placement at a certain distance. So we don't allow it to place it too close to the user, it will turn red. And only if it's at a certain distance, it turns green. And what that ensures is that this tire will be fully in the screen and it won't be cut off at the top or the bottom, right? So, and then the user, if they want to see it bigger, well, they can just walk closer, right? There's no cable, just walk closer. And then they don't even recognize that it's cut off at the top or the bottom because it's providing a better user experience. Yeah, let your apps live in the real world. Well, you can always have this kind of augmented reality virtual content floating in front of you, right? But with these devices, we actually know where surfaces are. We know there's a table and so on. So position your content on that, right? Use the real world and attach it to it. Also use stuff like this one, what I mentioned earlier with the model targets, right? I mean, augmenting real world objects, that's what it's all about in the end. So don't use just a virtual reality kind of paradigm for augmented reality. Yeah, let it focus and stay anchored. So basically there's two APIs here, which are often overseen by developers. The most important one is the stabilization plane. And that applies not just to the HoloLens, but pretty much any head-mounted device or augmented reality device. Basically what they do is there's a 3D plane, like a point in the normal. And every object that intersects with that plane is the most stable one. So basically this is where they optimize the rendering to be most stable. And what you want, of course, you want to have your 3D objects aligning with that. With the device portal, you can actually see and debug that. So here's where I'm showing you the device portal in the picture-in-picture. You can see I'm actually enabling show stabilization plane. So you can see the stabilization plane there. And as you can see, when I look to the right, it snaps on the dog, right? So it won't move. It will actually snap to the dog. So even if I walk a little bit around, this dog 3D model will be the most stable one, right? And that's pretty important. The good thing is with Unity 2017, they enabled depth buffer sharing, which basically means it can be done automatically. It will read out the rendering depth buffer, will find the closest object, and will automatically set the stabilization plane at this position. But you can also use an API called Focus Point. Another very important one is world anchors. You can also find it on ARKit, ARCore, Magic Leap. They call it persisted frame something. But basically it's a world anchor. And what this is, a world anchor means you can assign its own coordinate system for a 3D model, right? And what it does is basically the runtime will optimize that this 3D model will stay in its position, relative to the real world. So even if it loses tracking, you hide the sensors, go out of the room, go back in, it will readjust for the drift, and it will put it back into the position where it was before. And the nice part about it, you can even persist those. Here again, with this mixed reality view and the device pool, you can actually see them and debug them, right? So you see those little gizmos here. These are the world anchors attached to the dog. This one on the left side is for the cat. So it's a good way to debug those. All right, share your holograms with the world. Well, you can record videos like the one I've shown you, the mixed reality capture here, for example. That's directly recorded on the HoloLens, right? So it's using the camera, the little tiny camera that is in the front of the HoloLens. And what you can notice is it's quite grainy. The camera is really not great that they have on the HoloLens, like the webcam, if you will. Also, another downside is the blending is actually not what it will look like with the HoloLens. And another thing is, it of course does real-time video encoding on this device, so the frame rate will drop to 30 frames per second, right? So there's another solution called Spectator View, or we call our solution Mixed Reality Observer, and that looks a bit better. What we're doing here, basically, we're using the HoloLens just for the tracking. So there's a real DSLR camera, or like this, a proper camera attached to it, and we render the stream on the computer, but just use the HoloLens for the tracking. And we just build a new version where we're not using the HoloLens for the tracking, but just the Vive. You might know the HTC Vive, and HTC Vive has those controllers, right? And there are also trackers available. They look like a little hockey puck. So you can use those also to find the 6 dots, like the position, the rotation. So we attach that to a camera, have a very small rig, and we can use that for, 3D positioning and recording these kind of videos. Yeah, leverage tribal knowledge. There are a lot of smart people around that know a lot about mixed reality development, and I made a little short link here. Of course, you can, go to the forums, ask questions there. They are quite good, but even better is the Holo Developer Slack channel. Lots of guys and girls are there that are really, really good, and they're always happy to answer questions. Mixed Reality Toolkit, open source project with lots of samples, scripts, shaders, all the stuff you need to get started. It's, like you can see, it's pretty good. It's mainly driven by Microsoft, but in fact, most of the community contributions are from the community. Like my colleague here, Stephen Hodgson, he's the main contributor to it. So that's really nice, to see this change at Microsoft, that they're really taking open source seriously, right? This is really mainly driven by the community. That was before they bought it, but yeah, I mean, it's a good change, right? You see the other stuff, like the forums from Unity, also good. Think outside the box. So that is a point I wanted to make regarding sensors, right? So we have a bunch of sensors with the HoloLens and can track the surroundings and all of that. That's super good. But we also have Bluetooth connectivity. And for example, you can use Bluetooth devices and connect with it. There's, for example, a device called the Mayo armband. That's an armband you can put on. It measures muscle contraction, right? So it can use gestures. So if you move the hand like this, it will recognize that. And you can connect that actually with the HoloLens via Bluetooth. So you can use a couple of other things, right? Because the gestures the HoloLens support like this and that, it's pretty limited, right? And you also have to have your hand in view. So when the device doesn't see your hand, well, it doesn't recognize those, right? So you can work around those with a couple of other things if you think outside of the box. Here's another early example we did with the Kinect. So we're using the skeletal tracking of the Kinect. You can see it here. Here's the Kinect. And that recognizes adjustments, joints here basically. And then this guy with the HoloLens, we can stream the input from the Kinect. We, of course, had to synchronize the coordinate system, and then we can have some overlays. The lag you see here is actually not from the networking stack. It's rather the Kinect skeletal tracking takes a couple of milliseconds, right? But you can also think about connecting it with smart home devices, right? You look at the stuff, it shows you contextual information, like or IoT, right, in a factory setting. Yeah, built for the whole mixed reality platform. Yeah, let me step back for a moment. So the HoloLens is a mixed reality device, right? But there are also so-called immersive mixed reality devices or occluded mixed reality devices. And in fact, I would call them virtual reality devices, but Microsoft calls them immersive mixed reality devices. So what you can do is you can actually build for the same platform. So here's an example. My friend Dong-Young Park, he implemented that for the mixed reality toolkit. So you see he's actually implementing two-handed gestures, so you can use both hands for very natural input, like rotate, scale, and so on, right? And that is running on the HoloLens. But he can use the same APIs also on immersive mixed reality headset, where he's using those motion controllers, right? Same APIs, and this is really nice because you can, ship the same binary, basically. Of course, for this virtual reality setting, you want to have a virtual environment because, like, you don't see the real world around you. But the good news is you can also dynamically detect in what context it basically runs. But yeah, think about the whole platform. Well, most importantly, that doesn't just apply for mixed reality. That I think applies for development in general. If you're not familiar with it, definitely learn about deep learning. And that's something that will dramatically change how software is written in the next couple of years. Some folks even say it's software 2.0. And it's not about like, you don't need to become a researcher, right? You don't need to like create all those crazy models and come up with that. But you at least need to have an understanding. What is a convolutional neural network? How do I interpret the output data, right? Why is it the input data and that certain kind of size and so on? So definitely you want to make yourself familiar with these concepts, because you can use those tools like WinML, or on other platforms like on Android you have TensorFlow Lite. They take a lot of the load away, but you still need to know how to interpret that data, right? So definitely make yourself familiar. Couple of links. These are really good one here from Brandon Rohrer. He put up some really good YouTube videos. They're just like 20 to 30 minutes. And he explains, neural networks and also convolutional neural networks very, very well and very nice and visually. Even better is actually this one from the recent SIGGRAPH conference, the deep learning course here. That's 3.5 hours, quite long, but this gentleman is a very amazing presenter, and he actually presents all those concepts in depth without using any math or code. So I would highly recommend that. It's a really good one. Couple of other things, my blog, my Twitter handle, so you can find the slides and all of that stuff on my blog rather soon. The demo code I've shown to you. Here's a sample for Custom Vision AI. So Custom Vision AI it's a product from Microsoft basically, but you can also find competitors that have similar offerings. So this is really nice because it's basically a website. You can upload a bunch of photos, label them, hit the button, train. It will run the training for the neural network. You can even evaluate and see how good it is. Really nice user interface. And then you can export it as an ONNX file. So you can export it and use that in your custom vision recognition with Windows Machine Learning. And there's also a nice sample up there which shows you that end-to-end. A couple of my other talks which are more introductory to the topics, because this one was a bit more in-depth, as you might have noticed. And the other links I mentioned. All right, here's my contact info. If you want to reach out, connect on Twitter, LinkedIn, whatever. I'm also around probably for the happy hour in a little bit, so feel free to reach out, ask questions. I don't know if we have time for the Slack questions or if there's some. We have some? All right, well, with that, let's go into questions. But first of all, thanks, guys. I hope that was a good closing.
Yeah, thanks, René. So there is one question actually only. What would be the minimum internet speed requirement to have meetings with no breaking? Like it was probably for the first part of the.
For HoloBeam?
Yeah.
5 Mbit, really. That's what we use. With 5 Mbit, so that's really the thing. What we invented there is we can have not just the full HD video from color, but also the depth data to that with just 5 Mbit, right? As you saw, it's of course a bit more lo-fi, right? It's not your high quality. It's not a full 360-degree capture in real time, but that would require 50 Mbit and a whole crazy setup of cameras, right? What we use is really just one single camera, and we can stream that over a normal internet connection. And yeah, 5 Mbit is pretty nice, I think. And typically, I mean, I'm from Germany, right? You guys have much better bandwidth and broadband here as we have in Germany, so we had to get something with 5 Mbit. All right, before we close up, let me just quickly take a 360 video. Just look into that. That's a 360 camera, okay? So let's find a nice background, like maybe here. All right, guys, just look into that. Awesome. I will shout it out in Twitter, and maybe you see it tagged as DevTernity 18, right? That's the hashtag. Yeah. All right. Yeah. Thanks again. Enjoy the rest of the keynote, and then happy hour with a beer.